All right, so today in class, we're going to cover the so-called comparison tests. And there's two separate comparison tests that we're going to discuss. But before we dive into them, I just want to bring us into context of reminding us where we're coming from so far in the class. So in our journey for series convergence and divergence tests so far, we really have sort of three in our toolbox. We have the so-called test for divergence, the geometric series test, and the integral test. So just to remind ourselves, the test for divergence helped us basically throw away some series that right from the get-go looked like they were divergent, but it didn't capture all divergent series, nor could it tell us whether a series actually converges. So we started introducing other tests to let us know when a series converges or if it ultimately diverges. And that's where the geometric series test started. And the geometric series test, well, the unfortunate thing there, it only worked for geometric series. So if a series did not have this very specific form, we couldn't apply the geometric series test. And that brought us to basically last time introducing what is called the integral test. And the integral test was special because we could apply it to a much broader class or array of series in general. However, an unfortunate thing with the integral test is we have to actually compute an integral. Sometimes those integrals could be impossibly difficult to compute. And this is where the comparison tests really come in. So the comparison tests are another way for us to test whether a series converges or diverges, but test a more kind of general broad class of series in this way, similar in the vein of the integral test. However, the comparison tests will let us bypass having to do a difficult integral. So there's two separate comparison tests that we'll talk about. One that I'm calling a so-called traditional comparison test. And we're going to literally try and see, hey, how does this series compare to this other series? Which one do we know to be larger? Which one do we know to be smaller? Really starting to set up inequalities. The other comparison test, we're going to use and build up in this way of thinking, hey, this series looks awfully similar to this other series, but there might be some small minute changes between the series functions. And in those types of cases, we're going to introduce what's the so-called limit comparison test. And as you might guess, there is going to be a limit involved. Now, some of the things to note about comparison tests. These tests will only work for series with non-negative terms. So all the terms in our series have to be either 0 or positive. All right, we're going to discuss the benefits and drawbacks of each of these two comparison tests. Basically, we're going to introduce why do both of these comparison tests exist? Why not just one or the other? And the other thing we're going to see today is that many times the series that we're going to be comparing our series to will come in the form of either a geometric series or a p-series. And to give you a sense of sort of the idea of where these comparison tests are coming from, would be like saying, hey, if I know my series is less than a known convergent series. So let's put this another way. If we are wondering about a series, say some series a sub n from n equals 1 to infinity, and we know the following. We know that some other series, say b sub n, is convergent. And this is where the comparison comes in. And we know that our series function a sub n is less than or equal to the series function for b sub n. Basically, what we're setting up in that case by saying this last bit is that our series then from n equals 1 to infinity of a sub n must be strictly smaller or equal to the series for b sub n. But if we know that this series b sub n converges, because that again is something that we know, and if our series is smaller than that series, and the series must be positive, what that tells us is this series, a sub n, must also converge. So we're going to motivate these ideas in a lot more explicit detail. But really what this boils down to is the same ideas when we discussed improper integrals weeks ago and introduced that comparison analogy with Pokemon cards. If I tell you that I always have more Pokemon cards than you have, and I tell you I have 100 cards, well, that means you have less than 100. In other words, I have a finite convergent amount of cards, and that forces you to also have a finite convergent amount of cards because you have less than I have. And these are the ideas that we're going to play with in class today.